Yeah.
I may have lost track here, but I forget how this relates to work energy. Like, this just seems like we're confirming
Yep.
conservation of energy.
Yeah, she says, how does this relate to the work energy theorem? This looks like conservation of energy. So let me try to remedy that by considering the following experiment. So I have a mass here in a gravitational field, and instead of throwing it, I'm going to raise it up. Okay? So I'm just going to raise it in the vertical direction. Okay? Do I have to do any work on it in order to do that? Okay, so the definition of work, is it still up there? Yes, there it is, F dot dr. So if I were to isolate, I have mg down, and if that's the only force, of course, it's going to fall down, and gravitational potential energy is going to get converted to kinetic. But now I'm going to supply a force up for the thing that's sitting on my hand, so that might be a normal force. And in order to get it to move up, how big does n have to be? Say again? Greater than. Yeah? Really? Or equal? Okay, in the limit that n is exactly equal to mg, what will be the acceleration? 0, okay. So in the limit that I'm very patient, I could do that, give it just a little bump to start moving up, but then v will be constant and it'll just move all the way up. Okay? And it will have negligible kinetic energy. So the question is, how much work So by the definition of work being F dot dr, I would get that a little bit of work is the normal force dotted into the displacement. That is, this I would say is the work done by the normal force. At the same time as the normal force is doing work, how much work is gravity doing? Okay, it's going to be opposite. But I only want to consider the work done by the normal force. So I'll put a little subscript there. And now we can integrate. The normal force along this path can be expressed as a magnitude n times vertically up, a unit vector, y dot, or y hat, excuse me, which I now have to, what is dr vector? Yeah, well, let's be very, very general here. In principle, this could say you could go in any direction you like, right? So I could write it out as in the x direction, I take a step dx. In the y direction, I take a step dy. In the z direction, I take a step dz. So that looks like I have 3 integrals to do, except that having lovingly chosen a sensible coordinate system, 2 of them die. So this one, the dot product kills those, and I'm left with, well, I can even pull the n out of the integral because it's just a constant. So this is n times the integral of y unit vector dot y unit vector. It's a unit vector, so that's 1 dy. So the work done by the normal force will just be the normal force, times h, because I'm going to integrate from 0 up to height h. And as I mentioned, if I make the normal force just counteract gravity, then I never invest much in kinetic energy. So basically, I'm just stocking that work in the form of potential energy. So we get that the work done by the normal force is mgh. But mgh is something that we defined last time. That was the gravitational potential energy. So work could be transforming into kinetic energy. If I just take the unbalanced force and let it go, then I'm going to get kinetic energy out of it. Or I can do work against the force, and that gets stocked now in gravitational potential energy. So in the projectile example, I have no normal force. I'm not doing any work to change the energy of the particle as it flies, and so the energy is a constant of the motion. It's trading off my initial kinetic energy in favor of potential as it rises up, gets to a high point, falls back down. Okay?